Good afternoon and welcome everybody. This is our first at home of 2022. And of course we had hoped that we'd be at the IOP's, and we had of course hoped that we'll be at the IOP's headquarters, but you know, as we all know, that's not to be. The theme for today is of course safety critical systems, but within that it's really all about looking at risk and impact and mitigation, those sort of things. And we've assembled a, not sparing anybody's blushes here, some very high profile speakers to do this. And the essence of the whole program, that we've got 4 talks, the essence is to cover the spectrum of risk from high probability and lowish impact, and low probability, we hope, and extremely high impact. Our first speaker is Rod Muttram, Professor Rod Muttram. And you've all had a copy of his bio, but I've come to discover that, as with many short form bios, that certainly does not do justice to his very wide career. And indeed, that he has had the impact he's had on railway safety. And of course, the subject of his talk is railway safety or safety systems. Having spoken with him, quoting from my crib here, he started life as a control engineer, working mainly as a physicist, as the stability of particle beam accelerators. So he's got a reason to be with us today. And he's progressed then across industries at a very senior level. For nearly 30 years, he's been involved in railway systems as the engineering director of Railtrack, and since then wearing various hats responsible for national railway safety. Today, he's going to be talking about the inside story of railway signaling, some of the technology and the high-level politics that goes into that. The underlying theme of his talk will in essence be cost per fatality. You know, we'll hear about the science and all the rest of it, but at the end of the day, safety measures in all the specialist areas we'll be looking at, they cost money. And just as in the health system and so on, these things have to be evaluated and taken care of. So without further ado, Rod, if the powers that be can put you into play and show us your slides, we'd be very grateful to hear from you.
I appear to be able to share, so hopefully that's going to work. Can everybody see that?
Well, I certainly can. Full screen, you're there, Rod.
Good, great. All right. I've called this talk Risk Control in a 1 Degree of Freedom System. I'm assuming everyone is familiar with that terminology. An aircraft has 6 degrees of freedom. It can go forward and backwards, sideways, up and down, and it can rotate around any one of its 3 axes. A train isn't like that, however. The driver, from a driver's perspective, you have essentially only a brake and an accelerator. Everything else is controlled by the infrastructure over which you run. So it is a 1 degree of freedom system, and that constraint makes safety in the rail industry somewhat specialised. I'm going to start off by giving a general description of railway signalling, and I noticed someone called John Merrill had a very nice picture of mechanical signal box as his background. So to those of you who already know a bit about railway signalling, I'll apologise in advance for teaching Granny to suck eggs, but I had to assume that many in the audience would not understand what the constraints were on railway signalling. So I'm just going to take you through some of the generalities to start with. So historically, railway signalling was achieved by mechanical semaphores or coloured lights by the line side. So it's just coloured lights on poles, just like road traffic lights, isn't it? Well, no, it isn't. Why isn't it? Well, because trains have some very particular characteristics. Steel wheels on steel rails are one of the railway's great advantages. It gives a very low rolling resistance, and therefore it means very good energy efficiency, particularly for moving very large loads. And the American railroads are the biggest shifters of freight in the US and run trains with double stacks, and they haul over 10,000 tons sometimes on one train. But steel wheel on steel rail gives a very low coefficient of friction and thus a very long stopping distance, particularly if the rails are wet, giving you some lubrication, or contaminated with oil from dripping from the train, or sometimes we deliberately lubricate on corners to reduce flange wear, or leaf mulch, the famous leaves on the line. And of course, many tons on a contact patch, which is the size of a 5p coin, you can have in excess of 15 tons on that contact patch on a 5p coin section. And that leads to some other issues like the derailment that occurred at Hatfield, but that's another set of presentations and a completely different set of physics. So making that point again, trains don't have steering. Movable track elements called points or switches and crossings route the train, so a driver can't swerve to avoid a collision. So in safety terms, what that means with these very long stopping distances and low coefficient of friction, the maximum emergency brake rate in the standards for a UK train is 12% of G, 0.12 G. So from 300 kilometers per hour, the speed that's run on the Channel Tunnel Rail Link, the high-speed lines, that means you're going to take somewhere between 4 and 5 kilometers to stop. So that means even at lower speeds, stopping distances are well beyond the driver's visual range. So you need a signalling system that can tell the driver things about things that are happening that he can't actually see. You cannot rely on Mark 1 eyeball in terms of controlling the train in the way you can with a road vehicle. So that puts very different constraints on the signalling and control system than for road traffic lights. When I was at Railtrack, just to give you an example, the longest station overrun recorded when a train tried to stop at a station, the track was contaminated with leaf mulch and the driver actually managed to stop. Anyone like to take a guess? It was actually 2.5 miles after the station when he stopped, was the longest distance. So leaves on the line are not a joke. They're a very serious problem, and the railway spends a great deal of time and effort to try and deal with it. Before I put this in as a quotation that I spotted on LinkedIn, and I actually messaged the driver concerned and asked him if I could use it. It's a chap called Mark McElvray, who's a driver for Abellio ScotRail. He's a current train driver, and he posted this after the incident in the tunnel at Salisbury, when a train slid and a driver received life-changing injuries. And it really struck home with me from a driver's perspective, how annoying it must be to get these reports about silly, ridiculous reasons for train delays from leaves on the line. And from a driver's perspective, and I hope you've managed to read most of it by now, I won't read it out verbatim. When it starts to slide, you put the brake on, the speedometer drops to 0 because the wheels have stopped rotating, and you just slide. And there's really nothing you can do about it. You're a passenger too, but you're sitting at the front of the train just waiting for the collision, and that must be absolutely terrifying. There's nothing much you can do about it. Now, modern trains do have, as he says in his first paragraph here, wheel slide protection, the equivalent of ABS, and that's been around for quite a long time. And these days, certainly all the lightweight trains have sanders, and I wrote a standard that mandated sanders, and I'll talk about that in a minute. So they have a system that sprays abrasive into the wheel rail interface in the event of wheel slide occurring to improve the adhesion. But even with those systems, and the train at Salisbury recently had that system fitted, it had automatic sanders and wheel slide protection, but the train just didn't stop. And from everything I've seen, the driver did everything he should have done, but the train just kept sliding. And I first experienced this when I joined the railway in 1994. Pardon me, my phone is ringing. I hope my wife will answer it. Right, great. Sorry about that. My wife's obviously picked it up downstairs. One of the problems with presenting not in a venue but at home. So At Slough in 1994, it was a modern diesel multiple unit, modern at the time, of course, some time ago. So it's a lightweight aluminium unit fitted with anti-lock braking. The driver did everything in accordance with his training. He tried doing cadence braking. He was cycling the brakes, putting them on and off. The train actually in 1,200 yards, just over a kilometre on level track, after a shower of rain onto slightly contaminated track, he managed to reduce the train speed from 56 miles an hour to 30 miles an hour in that distance. And the train was fitted with a modern data recorder. So we had accelerometer readings and we were able to calculate the coefficient of friction. And it was incredibly small. There were a lot of zeros before you got to a digit. And we calculated that if he hadn't hit the buffer stops, which he did, he'd probably have gone another kilometre before he actually stopped. And the train actually ended up going through the buffers and into the booking hall. Luckily, no one was killed. That's a picture of the train sitting in Slough Station. And after that, by then, when I moved into the Railway Group Standards position, wrote a standard, and all those sorts of trains now are fitted with standards, but it doesn't always help. Network Rail also spends a considerable effort cleaning the rails and conditioning the railhead. There are trains, small trains, you'll see them on the network, called multi-purpose vehicles. They carry different packs on the back. They can do water jet cleaning. Some of them have wire brush cleaning systems. Water jet seems to be the preferred these days. They also carry a gook called sandite, which is sanding glue, which is actually put onto the railhead under slippery conditions to give the rail better adhesion. That coating and the coating of leaves can also form an electrical insulator between the train and the rails. And when we come on a little later to how the signalling works in terms of what are called track circuits, which tell the signalling where the trains are, that can also be a problem. And trains can disappear in the leaf fall system off the signalling system because they simply no longer, despite the fact they might have multiple axles, the axles don't connect the rails together anymore electrically, and that causes another problem. So we had the collision in Salisbury last year, which reminds us those risks still exist. So how do we manage these slippery beasts? Well, one of the core parts of a signalling system is called the interlocking, and the thing that John Morrell had behind him was a mechanical lever interlocking. So whatever signalling system is used, it has to provide drivers about things that are happening beyond their range, take account of those long braking distances, and it must interlock possible routes to prevent conflicts, because in a train approaching a junction cannot brake in time to avoid another train crossing its path unless the speeds were severely restricted because of these long stopping distances. So we interlock the routes to prevent conflicting routes being set. And that's why it's called an interlocking. So the core system of any railway signalling system is the interlocking. And they were originally mechanical. The technology then moved up into electromechanical relays, which are still deployed very heavily around the world. There are still many mechanical systems. But these days, signalling systems are largely computer-based. And that was pioneered both in Sweden by Ericsson and in the UK by British Rail with the SSI system in the 1980s. Many older technologies are still around, and in India, for instance, they recently, about 10 years ago, they re-signaled Delhi main station in relays simply because they feel more comfortable maintaining that technology than the computer technology, although many of their metro systems now use computer-based interlockings. So just some pictures of some interlockings very quickly. Principle there of the tappet interlocking, you can actually see how that works. When one locking bar comes down, the notch allows the tappet bar to the tappet bridle to slide across and release some of the other bars. So you effectively interlock the vertical movements with a horizontal movement. Sets of relays there, a bit harder to see. Some railway signalling relays are quite specialised, so we use things called force-guided contact relays, where you can't physically weld the contacts to get into a lock state, which would be unsafe. We also sometimes use gravity drop relays, where in the event of a failure of the electromagnet, the relay will gravity drop to a safe state. So some quite specialised relays used. But these days, largely, we use things based on computers. As I said, pioneered in the UK by the SSI and in Sweden by Ericsson. And the top two interlockings, the Westtrace and the SmartLock, are both more modern derivatives of the SSI system. And the one at the bottom, which I worked on when I was at Bombardier, called Ebiloc, Alstom have recently taken over Bombardier, so it's now an Alstom system as well. That derives from the Ericsson system developed in Sweden. So they've got quite a long pedigree going back into the 1980s. In an interlocking, a route can be requested. It might be requested by the signaller asking for a route, or on a modern computer-based system, they quite often have automatic route setting, which has the timetable programmed in, and the system will automatically set the routes of the timetable. The interlocking will check that the requested route is clear and then set and lock it. And the route can only be released when a train enters and passes through it, or there are very strict conditions when an emergency route release command can be issued by the signaller, but that's all very carefully controlled. So this is a safety critical system. So head-on crossing and converging routes must all be protected, and the logic can be quite complex. And an example here, and this is Derby Station, and at the top was the layout in 2017. This was then re-signalled in 2018, and the new layout at the bottom existed from October 2018. And if you look at the track layouts and the crossings and the number of potential routes through that, and the number of routes you would have to interlock for all the various points and route directions and dead-end sidings, etc., through that station, I think you can see that the logic controlling all of that to make sure you can't actually set a conflicting route where one train can run into another can be very complex. And if you get it wrong, this was very well publicised when Waterloo Station was being refurbished a few years ago. They didn't quite get the isolation of the part of the station that wasn't in use right in the interlocking lockouts. And the signaller managed to signal that train into the side of an engineering train that was sitting in the track because he tried to signal it onto that occupied track. Luckily, again, no one was hurt there, but some lessons were learned about controlling the elements of change, which should have been learned way back at Clapham in the late 80s, but somehow some of those lessons started to be forgotten. So interlockings are safety critical systems. The computer ones are normally based on a 2 out of 3 or a 2 times 2 out of 2 computing So in the event of a failure of the computer, the system will revert to the other computers. So in a 2 times 2 out of 2, one system will shut down, it will change over to the other system, and a 2 out of 3, normally the computer that disagrees with the other 2 will get shut down by the 2 that agree, and a flag will be put up for maintenance. The software in these systems is written to a standard which derives from IEC 61508, that is a specialised railway standard, EN 50128, and they're designed to safety integrity level 4, which is the highest safety integrity level under that standard. That standard contains recommended and highly recommended combinations of methods for reducing software failure probabilities to an acceptable level. And a number of coding standards and things are included in those recommended methods to achieve safety integrity levels at SIL 3 or SIL 4. And normally for a big interlocking it would be SIL 4, occasionally for rural routes where the train density is less and the risks are therefore correspondingly lower. You might have a SIL 3 system. And SIL 4 corresponds to 1 times 10 to the minus 8 to 1 times 10 to the minus 9 dangerous failures per hour, so a very low failure rate. Interlockings are therefore costly to produce and costly to modify because you've got quite a significant safety validation effort to go through every time you change the software. So you can imagine what the validation effort was like, for instance, for modifying the interlockings for that Derby station. You need to know where the trains are for the interlocking to set and release the routes and the signals. And traditionally that's been done by a block system. So you have blocks in the track, so divided into block section, and only one train is allowed into one block at any one time, except with special controls. Occasionally you can have a situation where two trains can be allowed into the same block under very special conditions, under very careful controls, but normally it's one train per section. That control might be procedural, and you can see this, I think, in the back of John Morrell's background. You can see some block instruments, which essentially are ways of signallers telling another signaller there's a train on the line. But they're normally supported by some kind of equipment or engineered system. So when you have a procedure, you might have some forms to support it. You can have token working where you hand over a baton or a token. So there's only one token and only one driver can hold the token at any time, and he passes it between the signallers. But most commonly you will have track circuits. So the rails are divided into electrical block sections. There's a transmitter at one end and a receiver at the other. And when there's no train in the section, the receiver can see the transmitter. When there isn't a train in the section, it can't. So it's a fail-safe system. The receiver fails and can't see the transmitter for some other reason. It will tell the system that it's occupied and assume that a train is there. I've already explained that leaves on the line might interfere with that electrical circuit, and we do lots of things to mitigate that, which again is the subject for another talk. But EMC is also an issue. When I first joined in 1994, we'd got these Eurostars coming into the UK, and you'll remember that when they first started running, the high-speed line wasn't finished, so they ran up on the conventional railway from the Channel Tunnel to Waterloo. And all of the track circuits down that section, which is DC railway, it's 750 volt DC power system. The track circuits there are AC track circuits because of that DC traction. And they were old enough that they were largely based on vane relay technology, electricity meter technology. And the Eurostars are quite capable of producing quite large amounts of 50 cycle interference. So we had to change a lot of the track circuits down there to much more sophisticated track circuits based on fast Fourier transform analysis of a step staircase waveform transmitter. So big upgrade in the technology was required because of that change in the trains, where the trains potentially could interfere with the old signalling system. And EMC is always an issue. You may have seen recently the new trains for the Isle of Wight, which were some modified destock off London Underground, didn't run because of software issues, and that's all associated with making sure that the traction currents, the return of the traction electricity down the rail, doesn't interfere with the signalling detection, which also uses the rail as conductors. So you've got a fairly big common mode problem there with thousands of amps of traction current and a few amps of signalling current, and you've got to be able to discriminate one and the other. So EMC in railways is quite a big issue. Recently, the last sort of 10 years or so in the UK, these were developed on mainland Europe, but Network Rail has been implementing them on a number of its routes. We use magnetic axle counters, so they count the train wheels into and out of one of these sections. It's a robust system, but it's not fail-safe. If you get a miscount, then you can get a section showing unoccupied when it should be occupied. And resetting it, in the case of a false count, is quite a complex procedure. And there was an accident in 1992, I think, where two trains collided in the tunnel under the Severn when an axle counter, because they were using axle counters there quite early on because of the amount of water there is in that tunnel interfering with track circuits. The axle counters were reset incorrectly. Two trains got into the section without the signal knowing they were there, and one ran into the back of the other. So axle counters need some quite careful management, and again are a safety system in their own right. Having that block system impacts capacity because you can only have one train in a section at any time, and it also to some degree constrains maximum speed and cost. The physics of the transmission of the signals through the rails and the leakage through the insulated barriers between the rail and the chairs and the sleepers means that you're limited to about 2 kilometres for the length of a track circuit. That's about the maximum block length. If you want more capacity, you'll have much shorter blocks, but that of course drives up the cost in terms of the numbers of transmitters and receivers. With only 2 signal aspects, a green and a red, train speed would have to be limited to the speed at which the train can stop at the red signal. So to overcome this, in the UK, we use multiple aspects that show block occupancy. Now on the continent, they use aspects to show speeds, and that has been quite a big issue in trying to translate technical systems from mainland Europe to the UK. Mainline routes use 4 aspects. 5 were used for a little while on the East Coast Main Line to try and get to over 125 mile an hour running, but I believe those have now all been decommissioned. So UK signals tell the driver what's happening in front of him in terms of the blocks ahead, but the driver needs comprehensive route knowledge. He needs to know where the signals are. He needs to know his route, and that's one of the reasons why UK driver training takes so long. A driver needs very comprehensive knowledge of the routes over which he's going to run to be able to interpret what these signals are only tell him the state of occupancy of the blocks in front of him is. So, as I've said, mainline European practice is different and tends to actually mean different speeds for different combinations of aspects. So just to look at this 4-aspect signalling sequence, you can see that you've got a green, you've got 2 yellows, a single yellow and a red. So as the driver approaches those, green tells him that he's got to proceed. The next signal will also be proceed, although it might be yellow. So two yellow signals means proceed, but be prepared to find the next signal displaying 1 yellow. And then if you get 1 yellow, that's proceed, but that's a caution. Be prepared to stop at the next signal because that may be red. It also may not be if the route clears. And then obviously a red signal means stop. Now these of course are shown in this diagram very close together, but the signals may actually be a very long way apart, and there may be track obstacles that prevent you from seeing them for quite a long time. Now that has a number of potential downsides in that if the route does clear, if this is approaching a junction and the train in front of you has actually gone down a different route, excuse me 1 second. Sorry about that, I have a noisy boiler in this room and it's just started up. If the train in front gets routed by another way and the route clears, then the driver of the following train won't know that until he can actually see the next signal and see that it's cleared up. So that as well is a limit on capacity depending on the route geography. That's one of the reasons why you want to do something a bit more sophisticated in the future. So all of that is about providing the driver with some information via the line side signals. But you will all be aware, I'm sure, that we've from time to time had accidents where drivers have not obeyed the signals and there's been an accident, and that's been known. And after Ladbroke Grove, I think this came into quite high profile public parlance. When we pass a signal at red, we call it a signal passed at danger, or a SPAD for short. SPADs have a range of consequences, from nil, you may go a little way past the signal and nothing happens, to something quite catastrophic. If you pass a red signal and come into conflict with another train travelling in the opposite direction at high speed, then a very nasty accident can occur with significant loss of life. So enforcement of the signals has been an issue for some considerable time. When signalling was first introduced, obviously it made roads much more safe than then there wasn't. But accidents still occur when drivers didn't see signals, sometimes because of poor visibility and fog, sometimes because of human error. And after the Harrow and Wealdstone accident in 1952 with 112 fatalities, BR started to roll out something called the automatic warning system. Now, there was an earlier system of a similar nature on Great Western, but it never saw national service. So I'll concentrate on this one, which I inherited in 1994, still not fully deployed, just to give you some idea of how long it can take to do these things on a big network. So AWS is a warning system. It was developed really for 2 aspects, but it was stretched to 3 and 4. It's a very simple magnetic interface, a fail-safe magnetic interface. So the train reads an electromagnet in the track and a permanent magnet in the track to tell it whether the signal ahead is green or something else. It can't tell it whether it's one aspect, one yellow, two yellows or red. It simply tells it it's not green. So it's green or not green, proceed or not proceed. It gives an audible warning, a buzzer in the cab if it's not green. If it's green, it rings a bell. And if it's not green, then this sunflower indicator that you can see in the center here turns from black to this black and yellow to remind the driver that he's not running under proceed signals anymore, so he should be looking out very carefully for the next signal. Now, it's a very good system, but it is only a warning system, and the driver has a cancel button, and if he presses that cancel button on a yellow signal, that's valid, and he should be doing that to go past his caution signal. But he can also cancel a red signal. And under repetitive running in dense traffic, you can get repetitive behavior where the driver effectively just keeps cancelling and cancelling and cancelling. And I'll come back to that in a second. So it draws attention to the signal, but it's stretched on multi-aspect routes, and it doesn't improve capacity because the communication is an electromagnet very close to the signal, just in front of it. It's an intermittent system, so it doesn't really give you anything in terms of capacity. It's a prompt to the driver. And when I inherited the rule book from British Rail, it was quite clearly shown in that rule book that it was the driver's responsibility to drive the train. And if the AWS system failed, the driver didn't have to do anything unless it was foggy. And if it was foggy, he simply had to drive at reduced speed. But there was nothing to say how this safety system should be managed, and we changed that later, as you will see shortly. So the first accident that started to impact on the way this system reviewed was Purley in 1989. It was very traumatic. The Mark I coaches weren't very crashworthy, so they tended to crumble like matchwood in an accident, as they did at Clapham. It was on a high embankment. It took 5 days to clear the wreckage. 5 people died and there were 88 injured. And it was a SPAD. The train from Horsham to London was hit behind by the Littlehampton to London service, which passed a signal at red. So ACCA SPAD. The driver of the Littlehampton train, the following train, the train that SPAD, pleaded guilty to manslaughter and he got a 12-month jail sentence. That was later commuted to 6 months and then reduced to 4 months. Sorry, it was 6 months suspended. It was later reduced to 4 months on appeal. That's just a few pictures to show you what happens in one of these accidents if you get coaches rolling down an embankment. Clearly, it's an absolutely catastrophic accident, a very high-risk situation, a very high-consequence situation. So when I took over in the 90s, the team that I had, one of the first things I got them doing was doing some analysis of risk concentration, because it was clear to me that BR had been managing these risks as fairly uniform, but of course it's not. The risk associated with any particular signal is very different depending on where it is. If it's controlling a high-risk junction and you miss it, then there's a risk of very high consequence. If it's out on plain line, then the chances are that the risk is much lower. So risk is concentrated. And there will be other things like signal sighting and the geography that will affect the risk of the signal. And the signal at Purley, we found, had been passed at danger 4 times in the 5 years before the accident, which is way, way, way above the all signal average. So it was quite clearly a high-risk signal. And after Southall, which I'll come to in a moment, I set up a human factors team in the railway, the first one there'd been. And the human factors analysis of AWS showed that drivers would come to rely on it. They'd come to rely on these audible signals. It wasn't really a driver's aid only, it was a safety critical system. So there was a significant risk of this unconscious repetitive behaviour occurring. It wouldn't be something the driver could particularly well control. And in 2007, that driver's conviction was quashed as unsafe and he was pardoned. A more sophisticated ATP system, automatic train protection, something that would actually stop the train if the signal wasn't observed, became a recommendation of Anthony Hidden, now Sir Anthony Hidden's inquiry into the Clapham accident. Although Clapham in 1988 was not actually ATP preventable, it was a result of a wiring error in the signalling under a renewal. But it was a recommendation. Now, automatic train protection is a much more sophisticated system which transfers information from the track to the train and enforces signal compliance. That usually means it has an onboard safety critical computer. But there are simpler systems like the TPWS system I'll describe in a minute, which can just use only hardware. So electronic hardware, generally a system of timers, but generally you need a computer. The simpler systems are intermittent. The more complex systems may use continuous communication, and there are various means of doing that continuous communication. Early systems used beacons in the track, and we still tend to use those beacons now, although they're generally just position markers. Cable loops, so you'll see on London Underground, the CellTrak system, which is used there, uses loop cables. You can see the wires threaded along the side of the rail. Or you can code the track circuit. You can put into the transmitted signal into the track circuit a code that the on-train system can read, normally through a coil system on the train. And if it's continuous communication by radio, which is becoming more and more common, particularly on metros, then we get this thing called CBTC, Communications-Based Train Control, which you will hear in other places. And that's generally the most preferred system for metros these days. High Speed 1 in the UK and the French High Speed network use a system called TVM 430, which is a coded track circuit cab signaling system with ATP. So back in the 1990s, BR started experimenting with these ATP systems and installed two pilot systems which I inherited. One was based on ACEC from Belgium, now Alstom, a system called TBL1, which was a beacon-based system, and that was on the Great Western Main Line. And parts of the Chiltern Line were fitted with a then Thales system called CellCab. So it was then Standard Electric Lorenz, now Thales, called CellCab. Also working with GC, and that was a system that became known as CellTrak, and was installed on the Chiltern. The intent was to select one for national fitment because Clapham Inquiry Recommendation 46 said BR should conduct these trials, and then once it had selected a system, it should deploy an ATP system across the whole network within 5 years. I think with the knowledge we have now, that was an utterly unrealistic expectation. It simply could not have been done at that speed. Both those systems were designed in a speed-based signalling environment on mainland Europe, as I have described, and fitting them in the UK proved to be really quite difficult. And the pilots did not run terribly well, but we learnt an awful lot from them. Now, in parallel with that, one of the other Clapham Inquiry recommendations, Recommendation 48, was that BR should develop a cost-benefit analysis system for prioritising safety investment and ranking it against other investments, whether that safety investment was worth it. And again, that was one of the things I inherited when I took over the job. So in 1994, my first year in Railtrack, I and David Rayner, who was the Director of Safety that I took over from, went to the Houses of Parliament and presented the then Secretary of State, Brian Mulwiney, with this report, which did the safety cost benefit analysis for ATP based on the two pilots, and showed that the cost per fatality avoided, and I prefer that to the cost of life, or the cost of a life, it's the cost of avoiding a fatality for this system was between 12 million and 14 million. With the benefit of hindsight, that number was underestimated. A full ATP system meeting the current standards will cost considerably more than that if you only look at it from a safety benefit point of view. Of course, it has other benefits potentially in terms of capacity of running the railway and therefore commercial benefits. But in safety terms, it's a very expensive system. That is way above the benchmark for public safety investment. At the time we did it, the Department of Transport used to use a two-tier system. Now it only uses a single-tier system. And for a multi-fatality risk, like a train accident, at the time the benchmark was 2.4 million. It's less than that now because they only consider a single benchmark which was based on the old single fatality risk of 1 million at that time. And I haven't looked it up recently. Last time I looked at it, it was about 1.8 million per fatality avoided. Now, if you spend more than that, potentially you are spending public money that could be better spent on other safety investments elsewhere. And there are lots of road safety schemes which can be achieved for below the benchmark that have not been implemented for lack of funding. I'd argue filling some of the potholes in at the moment might help quite a lot. I've seen several nasty accidents where cyclists have been killed due to potholes. So the Secretary of State decided ATP rollout would not proceed. And I for Railtrack and Peter Watson, the late Peter Watson, then for BR, who was the last engineering director of BR at the time, or was the engineering director at the time of rail privatisation, we decided we couldn't do nothing. So we commenced a new system development based on giving targets to meet that 2 million per fatality avoided. So we put out a specification that said it must meet that target. It must be simple and quick to retrofit, because a lot of the cost came from the retrofit costs, especially to the rolling stock. We were talking about a week to take a train out of service as a minimum to fit a full ATP system. We got to the point where we could fit this new system to a train in a single overnight shift. We did that by enhancing AWS and making the new system be bolt hole to bolt hole and connector compatible with just a few add-on bits and pieces. It is an intermittent system, and it was based on risk assessing and fitting it only at the high risk signals. So we went out to competitive procurement. A company called Redifon MEL, and now part of Thales, won the contract to fit this, with adding a non-overridable train stop and a speed trap to the AWS system. It was based on loop communication with low frequency loops and a very simple onboard system just based on timers. So it directly replaced the old AWS control unit, bolt hole to bolt hole and connector to connector, with the addition of just a small control panel with only lamps and buttons, a small additional antenna under the train, and a minimal amount of new wiring. As I said, we were retrofitting trains in a single shift. It's very simple to program from the track. You set the speed trap simply by the distance between the loops. So you set the speed with a tape measure. It's very, very simple to do. So the cost of retrofitting the infrastructure was also quite low compared with a full ATP system. And the cost was obviously further controlled by the fact we only fitted it at high risk locations, and developing a special tool for selecting which locations should be fitted. This is the system. If you ride around the system today, you'll see these grids everywhere. It's a piece of oil industry decking with a coil wound around it, which was the cheapest way to make it. Small company in Plymouth made all of those for us. That's the small control unit, goes in the train. You have an override, because under certain circumstances the signaller may allow the train to pass a red signal. You get a one-shot override. If the driver presses that button, he's allowed to pass one loop at stop, and then it resets itself. So you get a double loop in front of the signal to give a stop signal. So that's just the trigger and the release are on top of one another, and so it always says stop. And if it's a speed trap, then the loops are separated by a distance set by a tape measure. It crosses the arming loop. If it gets to the trigger loop before the timer on board has timed out, then it knows the train's going too fast and it puts the brakes on. If it's already timed out, then it's fine and it ignores the trigger loop and the train can just carry on. So it's just a speed trap in front of the signal. Now, that has some limitations, of course, because of where you can put the loops. And we found it was effective up to about 74 miles an hour. Above that, it only mitigates, it doesn't prevent. So you'll run into what's called the overlap. There's a fixed distance beyond the signal in which you won't get a conflict. Up to 74 miles an hour, it was fine. Above that, then you need to target what's called DPWS plus and fit some extra speed traps in front of that, which can extend that speed range upward. So you obviously still get some residual risk from the signals you don't fit. But it delivers 90% of the benefit of ATP for 10% of the cost. So we were going ahead to deploy it based on about a 7 to 10 year deployment scheme. and then the Southall accident happened. And this was a train running with the AWS isolated. The pilot ATP was fitted, but the driver, whilst he'd been trained, wasn't confident to use it because he hadn't used it for a while, so he didn't switch it on. And as I explained earlier, the rule book at the time didn't say he couldn't drive the train without it on. And so he drove the train on at 125 miles an hour with no protection system. By his own admission, he was packing his bag, not looking where he was going. He missed the double yellow, he missed the single yellow. He only started braking when he got to the red. And for 125 miles an hour, he was still doing 80 miles an hour when that happened. And that carriage that hit the electrification stanchion and crumpled, those Mark III carriages are very strong, but unfortunately one hit a vertical stanchion and crumpled up and 7 people died in that coach. And then just as the Southall inquiry was getting underway, Ladbroke Grove happened on the 5th of October, which was another ATP preventable accident on a line fitted with ATP, but where the ATP was not in use because when the Secretary of State made his decision, the commuter trains were not fitted with ATP. It was only fitted on the high-speed trains. So on a bright sunny morning, a driver missed all 6 signals across the track being red, ran through the signal gantry and hit a high-speed train coming the other way with a collision speed of over 200 kilometers per hour. 31 people died and hundreds were injured. The HST had gone past the ATP controlling signal, so nothing could be done to give the driver there any warning. The 2 drivers saw one another, but because of the braking issue I talked about, they managed to lose very little speed before they collided. He was an inexperienced driver. He was in his first week of driving unsupervised, and he passed that signal of danger. Many complexities. The inquiry was very critical of the management of that signal. In my view, it missed the fact that most of the SPADs at that signal previously had been misreads of adjacent signals. On that morning, all the signals were red, despite the fact that we had some work done by QinetiQ that said the signal conspicuity with the sun shining on the face should have still been enough for the driver to discriminate it. I still believe to this day that driver Hodder believed with the sun shining on the face of the signal that he saw a yellow or a double yellow and that he was authorised to pass it. But it was a very complex accident and clearly a pivotal moment again. The fire in Coach H, of course, was ingrained on everyone's memory. So I'm getting near the end of the time, so I'm going to just go through these last 2 slides. There were 3 inquiries. Most important here was the joint inquiry into train protection systems, which looked at this issue of whether we should fit this cheaper system we were developing or go straight to a full ATP system, which of course Council for the Bereaved and Injured was pushing for full ATP. I did not believe we could do that in a sensible time and believed in the system we were developing. The joint inquiry did recommend that TPWS would be continued, and I think the evidence from Sir David Davis, my chairman, and I was pivotal in that. But the inquiries did recommend the ATP system, based on the European standard, should be deployed by on the 3 main lines by 2008. I have to tell you the first of those routes, the East Coast Main Line, is being developed for deployment now in 2020. So 12 years after that date, it's still not been deployed other than on a pilot system in Wales. So I think, I was realistic about whether that system could be deployed in the speed. And I'm absolutely delighted we carried on with TPWS. We accelerated the deployment, and because it was a targeted system, we did complete that deployment on a risk-based basis in just over 5 years. We targeted 5 years, there were a little bit done after that. And as a result, Britain's mainline railway is the safest in Europe on most measures. And it's now 23 years since we had an ATP preventable fatality. Before that, you could just about say there would be some in every year. And in some years, there were many. So many people are alive today because of that decision to go ahead with that risk-based deployment of TPWS. So in conclusion, I hope I've given you a tiny taste of the complexity of the railway system and its control. There are many other things I could have talked about. It shows how one aspect of the implementation of a risk-based approach over the last 20 years has brought some significant benefits. I would say one of the other things that the Ladbroke Grove inquiries did was allow us to accelerate a number of the other measures that we were developing. Cirrus, the confidential incident reporting system, which we'd modelled on the system in the airlines, was being resisted by the train operating companies. Lord Cullen asked me to tell him which train operating companies MDs were resisting. And lo and behold, miraculously, by lunchtime the following day, they'd all signed up to Cirrus. And it has been implemented and brought great benefits. We recommended an independent accident investigation branch, which was set up, the rail accident investigation branch, modelled on the air accident investigation branch. So this isn't the only thing that's caused the railway to get much better. That risk-based approach has also led to some very specific improvements at certain signals in terms of their positioning and sighting as well. But this risk-based approach has moved us from being in the second division in terms of safety to Britain's Railways being one of the best in the world in terms of safety performance. And I'm very proud of what my team did in implementing this system and the fact that we argued to maintain it. Thank you. So I think I've been overrun by a couple of minutes, but I do apologise. I guess, Bill, any questions?
Yes, I'm there. I'm there, Rod. Thank you very much. I was trying to unmute myself. Thank you very much for that. We've had some very complimentary comments, but I must say I'm slightly lost between my ATPs and TPWSs and so on. But the overall message seems to be that it is not quite as easy as it looks, and especially when you've got you know, driver control in the middle of it. There is a question here which may be a bit topical, Rod, from John Belling. John, would you care to unmute yourself and ask the question? John? If you don't, I will ask the question.
Right, okay, I've unmuted. Can you hear me?
Yes.
Yes, John.
My question is about hacking into systems, which is topical. How susceptible is the computerized safety systems to hostile hacking, which could presumably take over the system and cause all sorts of accidents and so on?
Yeah, we are very aware of it in the rail industry. I won't say it's never happened, because it has. I'm certainly aware of one system I worked on. I probably shouldn't tell you where it is, but there was a computer convention right next door, and one of the guys at the computer section managed to hack the control system and take control of the vehicles, luckily without a safety incident. Most railway systems are closed, so the older interlockings are closed systems. They don't have an external connection to the internet. One of the issues with, of course, communications-based train control, where you've got a radio bearer, is the status of that bearer both in terms of intrusion and whether it's part of the safety system. And in mainline rail, this European system I talked about, ETCS, the European Train Control System, has a system called Euroradio, which is an encryption system which encrypts the signal that passes through the radio bearer. So the radio bearer has nothing in the safety chain at all, and the signals are encrypted. Now, there is still an issue that it's possible to have a denial of service attack, where because of the safety measures you put in, someone can interfere with the system and the safety measures will cause the system to shut down. So we're always striking a balance between using open systems and closing the systems. So I hope that's enough for now. I could spend hours talking about it, but yeah, we're very aware of it. It is an issue. There are encryption systems in most of these, and very often we use closed communication systems for that reason. But with radio, of course, it's much more difficult to close. You tend to use encryption, and you will use line of sight to some degree and low powers on line of sight to try and keep the radio zone for potential interference as small as possible. So yes, it's something we think about along with electromagnetic interference.
Thanks for that. Thanks for that, Rod. We'll take another question. Mark Molinares, I'll paraphrase his question if I may. And it's all about the visual bit. And he's essentially asking, how do you look around corners? With trains with a stopping distance, up to 5 kilometers, how is there anything in sight? Sorry, that's an unfortunate choice of words. No, is there anything round the corner, shall we say? Well, another unfortunate choice. How do we look round corners?
Well, you can't. That's why you use multiple aspects. To some degree, the yellow and the double yellow are allowing you to know the signal that you're approaching is likely to be red, and therefore you drive appropriately and should already be slowing down to a speed where you know you could stop, based on your route knowledge of the fact there is a signal round the corner. And that's why, as I said, route knowledge is very important. Now, you do use repeaters sometimes to improve the sighting. That's something that's done. At Ladbroke Grove, that signal SM109, because it had several SPADs before that, there'd been an investigation report, and the report had recommended putting in place coaxial repeaters down in the track, and that had never been done anywhere before. So the zone management were very reluctant to do it. So there are various measures you can take, but the great benefit of these radio-based ATP systems is, of course, you've got the signal in the cab, and the radio will immediately convey any change of aspect to the driver, and you're then not reliant on signal sighting. But there are standards for sighting, of course, where signals are lined up and you look at it. But this whole multiple aspect system is there because of the fact the geography means you can't always get a long line of sight to the signal.
Okay, I'm going to come up with one last question, but Rod, just to give you a little bit of comfort, there must be a number of train spotters in the audience. Now, I'm serious, because I've had one or two bits of chat that have come through to me that, I don't know about you, I hope they have, about excellent talk. Basically I'm a train spotter. So
I didn't have the chat up whilst I was talking, obviously. I'll have a quick look in a minute. I saw about a question about Crossrail, Bill.
Yes.
And if
we'll take that as the last one.
I'd like to give you a 1 minute answer on that.
We'll take that as the last one.
We could do a whole lecture on Crossrail, but back when they were looking at Crossrail initially, they got a consultant, an American consultant, to look at it, and he recommended that for the core system, because its capacity is very important, they should use a proven CBTC system from the metro world. So Crossrail is unique, and the government had to apply at the time for a dispensation from the European Union to use a non-standard system. So Crossrail actually has 3 signalling systems. To the east, it uses the TPWS system that I've just described to you. Through the tunnel core, it uses a system called TrainGuard, developed by Siemens, which is a metro communications-based train control system. And then from the portal at Paddington out to Heathrow, it uses ETCS, that new European standard system. Now, I've had many heated arguments with Andrew Woolston, who was the MD of Crossrail at the time the decision was made, that was a crazy decision. It should have used ETCS level 3, and we didn't have time to talk about the characteristics of ETCS today, but there is a communications-based moving block version of ETCS, which has not been yet used on a mainline railway, but that's what they should have used. And interestingly, on Thameslink, that has ATO over ETCS and is much better. But the introduction of all those extra interfaces, and it's usually the interfaces that add the complication, is why Crossrail is one of the reasons why Crossrail is running late, although the integration of the complex stations has also proved very challenging.
Excellent. Well, thank you, Rod, very much for that. As with train spotting, there's always a mixed audience. There are some that it's like Marmite, and Marmite seems to be having a resurgence from what I've seen.
Yes.
So it's like Marmite, and some people love it and some people hate it. And it looks as though we've got a number of people amongst the Institute of Physics, or at least our audience, that love it. So thank you very much indeed.